All right, I think we're about ready now. We'll get going here. We've got the real hardcore Java developers in here that are sticking around till the last session. Thanks very much for being in here. I'm going to talk a little bit about Invokedynamic. How many folks are completely baffled by what Invokedynamic really is? Okay, so if you folks have some idea what we're talking about, we'll dive into it and I'll give you a tour of how it actually fits together and what we can get out of it in the future. Basic contact information for me, currently at Red Hat. I've been working on JRuby full-time for about 6 or 7 years now, and kind of branching out now into helping out other languages, working on helping the JVM guys a little bit, and doing a lot more talking about the JVM and how it works, educating people on what's possible. I was also probably the earliest adopter of Invokedynamic when there were the earliest builds out that had even the pre-JSR implementation, pre-JSR APIs. We were already trying to fit it into JRuby, so I've followed the implementation all the way along, and I've got a pretty good understanding of how everything fits together. This is a tweet I had from a couple years ago, and I still believe that this is true. I really believe that Invokedynamic is by far the most important change that's happened to the JVM in pretty much its entire lifetime. And it opens up incredible possibilities for not just alternative languages, but for Java itself. For example, with Java 8 using Invokedynamic as part of the Lambda implementation. So you're going to see a lot more use of this in the future, and hopefully you'll be able to get some use out of it yourself. We'll talk a little bit about history. So the original JVM specification, the JVM specification authors, James Gosling and others, did have a mention of the possibility that someday the JVM might be a host for multiple languages. It wasn't really designed around the possibility of the language. It was designed for Java in the beginning, but there was a distinct possibility that that same bytecode set, that same VM, could run multiple languages. And over the years, language authors have done a lot of different language implementations. There's several hundred different language implementations today, and more are being created all the time. The problem, though, is that the JVM and the original bytecode set is kind of a mismatch for some of these languages. They had different ways they wanted to do dispatch, different sort of code structures that they wanted to have. Invokedynamic is kind of a way to move the JVM forward, give the language authors a little bit more power in controlling the JVM and defining how their language works on top of it. We look at some JVM languages through the years. JPython, which is now Jython, and Rhino were some of the earliest mainstream language implementations. Well before 2000 they were around and available. Even so, there was no real official backing of multiple languages on the platform until probably about 2006, when Tom Enebo and I joined Sun to work on JRuby. Around that time, the sort of stagnant Invokedynamic JSR got a reboot. It was placed in the hands of a dynamic language fan come hotspot developer, John Rose, and as a result, we ended up with a very nice implementation of dynamic dispatch, dynamic language support in Java 7, which shipped in 2011. So now what is this whole Invokedynamic thing? There's a lot of confusion about this, about what we actually get out of it. And a lot of people confused whether it even helps Java or is useful for Java and other statically typed languages. So first of all, most people think, okay, it's just a new bytecode, right? That's all we really get out of it. Well, that's not quite true. There is a bytecode involved, but there's also a lot of plumbing around it. There's guarantees that the JVM will make, and there's much more that we can do than just use this bytecode and just have that as the feature. So what about, is it simply a new form of invocation? It has invoke in it, so is it just for doing a different type of call system? Well, that's one use, but it turns out that it's very useful for many other patterns as well. Hopefully I'll be able to show some of those a little bit later. You'll understand why it's not just simply about invocation. Well, then surely it must be only about dynamic languages, because it even has dynamic in the name. It's an invoke dynamic. It must be for dynamic invocation. Again, that is one use and probably going to be the most common use of it. But there's a lot of other things that you can do with Invokedynamic above and beyond what dynamic languages need. So what I've been kind of describing Invokedynamic as is a user-definable bytecode. It's a bytecode that you get to define. You get to say how it actually performs what it's supposed to do, rather than just using one of the canned built-in bytecodes that already comes with the JVM. And in order to do this, Invokedynamic also comes with an API called method handles, which are basically method pointers, field pointers, plus various adaptations around them, branches, argument manipulation, and so on. So with these two pieces together, you can insert an Invokedynamic bytecode into a piece of Java code, into the class file, and the JVM will ask you how to actually implement that bytecode and what it should do at runtime. Now this is a little bit confusing, so we'll break it down into two parts. There's Invokedynamic is the bytecode and the specification, but really it's two pieces. The bytecode is the invoke part. That's what goes in the code and performs some sort of call. And the method pointers are the dynamic part, where you make up what that bytecode is actually going to do. And in JSR 292 terms, this is the bytecode plus a bootstrap method that the JVM calls to when it needs to find out how to wire this up, and the method handle API. So I'm going to show some code in these slides. All of this code is available on my GitHub project, Indie Deep Dive. You can play it with it and try some stuff out. It's easy to jump into it, start juggling around method handles, and maybe play a little bit with Invokedynamic too. So we'll start with method handles because it's the easiest thing for Java developers to wrap their heads around, since it is just a standard Java API. All right, method handles. So as I mentioned, they're basically function pointers, field pointers, array accessors. It's very similar to Java lang reflect method, Java lang reflect field, a callable object that you can use to invoke a method or to set or get a field, and so on. In addition to that, there are various adaptations. You can insert an argument into that call and have it always be available. You can do some flow control. And probably the most important thing about this is that unlike Java lang reflect method or Java lang reflect field, the JVM knows about method handles as an intrinsic low-level part of the VM. And so doing calls against a method handle or a chain of method handles that have been adapted will be much easier for the JVM to optimize. It's able to see a path through those calls that can be optimized back into the Java code just as if you were calling from one Java method to another. So in the ultimate goal here is that method handles will be significantly faster than using reflection, but when combined with the bytecode, basically just as fast as doing a normal static Java call. So the package we're talking about here is Java lang invoke. Three classes you're going to see in the upcoming slides here. Method handle is basically that callable function pointer, that callable command object, if you will. Method type is just a structure that represents the return value and the argument types for a particular method or for a particular method handle, just to represent what the signature of the call is supposed to be. And then the method handles class, plural, it provides utilities for getting pointers to functions, getting pointers to fields, and then doing all of these adaptations. So look at a couple quick examples here. First of all, the method handles.lookup method gives you a lookup object. And this is what you use to actually go out and get those pointers. You get a static method, a virtual method, and so on. There's also public lookup. And the difference between these two is that public lookup, the lookup object you get, can only access anything that would actually be public. So it's safe. It's as if you're accessing those things from outside the class. You can only normally get access to anything that's public and would be seeable from the least privileged location in the code. The lookup method, however, returns a special lookup object that can see anything you'd be able to see at this point in the code. So if I have a private method in my class and I use method handles.lookup, that lookup can give to anybody a callable pointer to my private method or access private fields. And this allows you to be able to wire up public and private fields and methods within your method handle, within your little command object, without having to do any special set accessible work, such as in reflection, or without having to build accessors and generate extra code and so on. So on the lookup object, there are 8 methods that are the most interesting here. The first 4 here, find static, find virtual, and find special, find constructor, are for accessing different types of methods in the system. You can find static methods, virtual methods. Specials would be accessing a private method, accessing a superclass method, and so on. And find constructor obviously gives you a constructor. And then by the same way, the field pointers give you getters and setters, just like a Java Lang reflect field object would. So here's an example. Up at the top, we've got some regular old Java code. No JSR 292, no Invokedynamic involved here. System.getProperty Java home, and print out a hello world. Below that, we see 2 signatures. These signatures represent the types of these 2 calls. System.getProperty, we're interested in the version that returns a string and takes 1 string argument. By the same way, print line, we expect it to return void and take 1 object. The next 2 lines are the lookup accesses. So we're getting access to those actual method handles that represent the getProperty method or the print line method. It reads basically as system.class, is the class we want to look it up from. GetProperty is the method we're looking for, and then we pass in the type. And same thing with print stream, print line, and the type that goes along with it. Now we have 2 callable objects that represent these method invocations, and at the bottom you can see that we're able to invoke them just as if they were a Java Lang reflect method or if we were doing the actual Java call. But with the hopeful guarantee that the JVM is going to optimize this much better than it would a reflective call. Now you might notice here at the bottom that there's a cast to object. We're casting a string to object, which is an unusual operation to see in Java code. Normally any object in the system can be passed wherever we'd want an object in a call, so this cast is kind of unusual. Now why do we actually have this here? These methods, this invoke method on method handles, is what's called signature polymorphic, which is basically a complicated way of saying that instead of just being whatever the target type is, whatever the target signature is, which in this case invoke would just be returns object, takes any number of object arguments, the caller determines what that signature is supposed to be. So if we have a method handle to a function that requires a string argument, then we would need to do a cast on the calling side to make sure our call types, our visible types, match what's in the actual method that we're going to call eventually. And it's a little bit complicated, and you're probably not going to run into it too often. You can use invoke with arguments and a couple other versions of invoke to get around this signature polymorphism, but if you see this in code, that's what you're actually looking at. It's basically trying to make the call side types match the actual types at the end of the method handle chain. A little bit more example here. Here we have accessing system.out. We're going to access the field directly with a system out method handle that does the field lookup for us. And then here with out3, we're able to make the invocation, get access to the field, very much like Java Lang reflect field would do for you. Here's an instance field that we're going to set. The example Java there, again, very simple. It's just a struct. We're just setting a value into it. And then we use lookup find setter to get a virtual setter, an instance setter for the name field, call it below, and pass in the arguments. All right, so we kind of got a good idea of what the basic pointer types that we have, method pointers and field pointers. We'll talk a little bit about the adaptations that we can do around them. And now normally, if you were going to do this with a Java Lang reflect method, you'd need to write your own little adapter code around every invocation to make sure you're passing in some predetermined values, to make sure you're doing exception handling, possibly to do a branch between 2 different methods. What the method handles API gives you is a way to bundle that all into the same function object without writing the code, without generating an extra class for a little command object, or without generating bytecode at runtime. You get it all in one little callable unit that you can pass around and not have to have this boilerplate everywhere. So as far as argument juggling, there's a whole bunch of different methods on here. I'm just going to talk about a couple of them. You can insert arguments, drop arguments. Permuting arguments is basically reordering them or duplicating them within the call path. You can filter arguments, which basically translates one argument out of the list before passing it down the line. Fold takes all the arguments in, does some calculation, and then continues from there on. And casting operations, which are fairly straightforward. You can also splat and spread these things out. You can turn multiple arguments into a var_args array, turn a var_args array into individual methods. Again, all the basic things that you would do in Java code if you were to generate it or write it by hand, but you can build this up programmatically as part of your little method handle object. So looking first of all at an insert example, say we've got a handle to the min method on math. It takes two arguments normally, but we know we're always going to be comparing it with integer.maxValue. Now, rather than having to always pass it in everywhere we do our invocation, we can insert that max value into the handle and get a new handle that only takes one argument. So it's grabbed this value, we've inserted it into the call, and it will always be there. Basically, like a partially applying values to this call. Example in Java code here. Remember, we've got our getProperty method handle that does the system.getProperty call. We've got our printLine method handle that does a printLine call. In the first case here, we always are going to just be getting Java home. That's what we're going to pass this object around to do. It's a Java home getter, basically. So we'll insert an argument at the beginning. So every time you call this, it already has the java.home string. Down below, you can see we call it. We don't have to pass any arguments in anymore because it's already part of our method handle object. For the print line, we know we always want to call it against system out. We basically want a system out print line function object that always just prints to standard out. We insert that into the argument list, and then we can invoke it down below, just passing in the string and not having to access system.out every time. Filtering I mentioned. Filtering basically allows you to translate one or more arguments in the argument list on their way through as they go past. So in this case, we've got our min example again, but we want to always test A over 2 compared to B, rather than just directly comparing them with their incoming values. So we can filter just the A argument, always have it called divide by 2 on that argument before passing it on down. And we get a new handle that does that for us as part of the call. That example in Java code, here we're going to make a version, basically an uppercasing method handle, an uppercasing function that we can pass around to anybody who wants to uppercase a string in the system. The example at the top, a simple Java function. Here's our little uppercaseifier. Doing that with Invokedynamic, we're going to get the toUppercase method off of the string class, which just returns a string value. We're going to cast it to object type so that we have the right types for inputs and outputs here. And then we're going to filter the first argument passed in, which is basically just the string we're calling it against, and make sure that we're always calling toUppercase on it. Then at the bottom, the last handle, the final filter here, we're going to actually have it print everything out at the same time. So we've got a single function object that will take the string in, uppercase it, grab system.out, and do the print line all in one object. All right. Folding is a little bit different. I don't have a code example for this, but it kind of helps to see what it looks like here. So say we've got a handle to method.min again, and we're always going to be just comparing A with A over 2 to see which is the lower of the two. Essentially kind of checking to see whether it's positive or not in a very weird way. So here, we're going to always compare A with A over 2 using our little divide by 2 method again. By doing the fold, we basically can strip out one of those arguments, create a new handle that only takes a single argument, divides it by 2 and passes that for the first arg, and passes it as the normal argument for the second argument. So it's all combined into one function object. All right. So flow control. The next thing you'll probably want to do after you've done some argument manipulation and argument juggling is possibly have some branch logic in your little function. There's two ways that you can do this in the method handles API. The first is a guard with test. It takes three handles. One of them is a Boolean branch that basically just returns one of them is a condition, essentially. Calls this function, gets the return value, Boolean, true or false, and then follows one of the other two handles that you've given it to basically handle the branching logic. And a switch point, which is a little bit more unusual, it's basically just an on-off switch that you can only switch off. Starts as true, you can switch it to false, and it stays there forever. I'll explain that a little bit more once we get there. So graphically, the guard with test, doing a branch based on some conditional Boolean returning function. Say we have two string keys, and we want to call one of two different handles, one of two different functions, depending on whether these keys are equal or not. So our test is at the top. That's our condition handle. That's basically just going to do an equals call, key 1 dot equals key 2. Depending on whether it's true or false, we follow the true path and print out yes, or we follow the false path and print out no. Now, in Java code, here is the example of regular Java code we might write by hand to do this. Again, if we were going to be doing this with Java lang reflect method, we might have to have this code in a few places. We might have to be passing around our own little generated function objects. In this case, we're just going to basically either uppercase the incoming string or lowercase the incoming string based on some random Boolean value, just to kind of demonstrate what we're testing here. All right, so the example with method handles, up at the top, we're going to grab our random Boolean function pointer, which basically just returns a Boolean object to us, either a true or false, randomly. We're going to guard our two uppercase and another two lowercase method handle. Remember those handles from before that take in a string and either uppercase or lowercase it. So guard with test, based on our up or down, which is randomly returning a Boolean. The uppercase path is the true path. The lowercase path is the false path. And that down at the bottom here, we're going to insert our system out print line back in there so that every time we call it, it's going to get a random Boolean, test whether we've got a true or false, branch to either the uppercase or lowercase, and then pass that along to the print line logic, all in one object. And down at the bottom, we do our invokes of this handle, and you can see that it randomly will uppercase or lowercase and print it out to the console. Again, no code generation involved, no extra little function objects you have to generate with bytecode or by writing little inner classes. It all is one object that does all of this in one little unit. Now the switch branch, this is kind of the standard way of showing it. So there's a switch that is either on or off. If it's on, we follow the true path and print out on. If it's false, we follow the off path and print off to the console. But a more practical example of why you might actually find this interesting would be some sort of caching logic. Is the data still valid that we've got in our cache? If so, follow the true path and return the data directly. However, if we find out that the cache has been invalidated at some point, we switch this branch off, always follow the false path, and then go and get the data again. And then possibly recache it, create a new switch, and go back to the beginning and with cache data again. The example in Java here is essentially the Java code that we're trying to get out of this method handle chain. We've got a little volatile Boolean that starts out as true. Based on whether that's true or not, we're going to follow the true path and uppercase the string, or we're going to follow the false path and lowercase the string. And we've only got one turn off method that can disable this. It can only be turned off. Here's the example using the actual switch point object. This is another class in Java lang invoke. We create a new switch point. We call guard with test on the switch point, giving it the true path and the false path. And as long as it's true, it will follow the true path, uppercase our string. Once we switch it off by invalidating it, say it's invalidating our cache, it will then follow the false path and always go lowercase the string here. So things like cache invalidation, a lock-free atomic Boolean, for example, things like that. A lot of cool things that you can do with this and have it optimized by the JVM and all in one little object without the amount of code that we had before. And now you're actually starting to see that the code size for method handles here is actually quite a bit less than just generating the Java code. So exception handling is a little bit more complicated to show in method handles, but I'll show you a more graphical example of it here. Java lang reflect method, it's possible that it may raise an exception. It's possible that the method it calls might raise an exception. And ideally, you'd want to be able to handle that exception the same way everywhere you invoke it. You could certainly generate a wrapper class or a utility function and pass it in there. Or you can use catch exception on method handles API. You give it the body of code it's supposed to run, an exception type you expect, and then a handler pointer to a piece of code that's going to take over when that exception gets raised. And then if you're going to be handling exceptions, you're probably going to need to throw exceptions. The throw exception method handle adaptation basically just throws whatever exception's been passed into it. So you can use this as your receiver for, I can't do anything with this exception, just re-raise it. So graphically, the catch exception logic, we've got some handle to a dangerous method that might raise an exception. We want to be able to handle it and wrap it up with another piece of logic. We do our catch exception, giving it the do something dangerous call and some handler logic, and we essentially get a single function object that does all of that try-catch logic for us, wrapped around the original handle. Okay. So onward to the other half of Invokedynamic, the bytecode side. So a little JVM 101 to start out here. There's around 200 operations, opcodes on the JVM. Depending on how you count, 10 or 16 of these are what I would call endpoints. They're ways that you're going to get data in and out of the system. They're ways that you're going to interact with methods. So we've got our invocations, virtual interface, static, and special. We have our field accessors. And we have array accesses, and this is where it's kind of depending how you're counting for the different array types, but basically loading and storing values from and to an array. So pretty much all Java code in the world revolves around these endpoints. The rest of the bytecode is just nonsense to get us from one endpoint to another. Get some data, print it out to the screen, make a database hit, juggling arguments around so that we can eventually hit one of these calls or fields or put something into an array or object somewhere. So the problem with this is that we've got these 200 opcodes, and you are pretty much stuck. If you need something outside that, like a different kind of method invocation, a different way of accessing a piece of data, you have to generate your own code potentially. Maybe that will optimize, maybe it won't. What we want to be able to do is tell the JVM about our different operations. Rather than having to add a new bytecode every time something comes down, every time there's a new way we want to do something on the JVM, we'd like to be able to program the JVM from our code directly. So the goals of JSR 292 is kind of to provide this user-definable bytecode. You have full freedom then to define what the behavior of this operation is supposed to be. You do that by wiring up these method pointers, wiring up these little method handles, and the JVM then, in turn, will go and optimize this as if it were one of those standard operations, as though it were a standard static call or a virtual call. And then you can redefine how the JVM does things, and we can avoid continually adding new bytecodes to the JVM as the latest and greatest language features come along. Another way of looking at this, here's a bunch of different calls. Static calls like current time millis, virtual calls, interface calls, and down at the bottom, special calls like doing a super invocation or a constructor. And these boil down to 4 operations. The 4 invokes here all have their own basic sequence of events that happens at the VM level. And largely these are kind of the same. Looking up methods, doing the invocation, caching them, doing some type checking. But if you need something that doesn't fit into this menu of options, you're stuck. You have to build it on top of these, wire up your own logic. Invokedynamic comes in and says, rather than predefining the sequence of operations that this bytecode will do, I'm going to let you decide exactly what happens when this call is made. So it calls your bootstrap method, gets some instructions from you on how to proceed, wires that back up into the code, and then continues to do your logic from then on, as if it were part of the JVM from the beginning. A little bit more graphic way to look at this. We've got our switchboard operator here. So we've got our Invokedynamic bytecode up at the top. A call comes in from somewhere. The JVM doesn't know where it's going to go. The JVM has to ask our bootstrap method, depicted on the left as our switchboard operator here. So it calls out to the JVM calls back to our code, which is in the bootstrap method. The bootstrap method wires up a bunch of method handles that says, do this branch, do this method call, translate these arguments in some way, and then eventually call printline, for example. The method handles then get wired up to some target method like printline. The JVM installs that logic right where the Invokedynamic bytecode was, and then the magic happens. After that first time, after we've given the JVM instructions on how to handle this Invokedynamic, all of the rest fades away. And from then on, it looks like a direct path from the bytecode to whatever chain of logic we've provided to it. And it's able to optimize it as if it was just a standard method call. So now we get into the combining of the two sides here and actually seeing what it looks like. So the tools I'm going to be using here, I'm using ASM kind of transitively through another library, and this is pretty much the standard bytecode library almost everybody uses now. So standard that the Nashorn JavaScript implementation uses it and is pulling it in a hidden package within OpenJDK 8. JITescript is a little fluent DSL API wrapper around ASM, removes some of the boilerplate code, a little bit less verbose. And InvokeBinder is a library I'm working on that essentially is a DSL or a fluent API for building these method handle chains. Makes the code a little bit more readable unless you kind of work with it more in the top-down direction as if you're doing the call yourself or writing Java code. So we'll look at a couple different examples. The first one is just a trivial Invokedynamic bytecode, does a bootstrap, wires up some target method. Very simple. Now you'll notice that there's a new type in here. This is Java Lang invoke call site. Call site is basically just a little wrapper, a little holder for a method handle. This is what the JVM stuffs back into the Invokedynamic bytecode at whatever point where it happened in the code, and then it pings that every time to see whether it needs a new method, whether it's been rewired, or whether it can go straight through and do the invocation, do the call the same way it did last time. And there's three types that are available for you. Constant is a call site that never changes. That's the one we'll use for this example. Mutable call site allows you to change that later on, so you can rewire it depending on what's happening at runtime. And volatile call site is basically a mutable call site with some additional guarantees about when that change will be visible. Okay, so here is the method we're actually going to call with Invokedynamic. Every time we invoke it, it's going to increment this counter and print out hello world number 1, number 2, number 3, and so on. Here is the JITescript code for generating our little class. The code block here basically represents what would be inside our method. We're implementing a runnable, so this is the body of the run method. We do our Invokedynamic, calling foo. That's the name of the method that we are passing. We want Invokedynamic to look up for us. The signature is just going to return a string. And then ASM has its own representation of an Invokedynamic handle that goes into the bytecode. I'll show you that in a moment. Once we've got that string, it's on the stack. We're going to print it out, and then it's run so it doesn't return anything. We'll exit the method. So here is the code generation side to get Invokedynamic bytecode wired up. The ASM handle here, very similar looking to the method handles lookup and method type logic. So it's going to be a static method, and invoke static is ASM's opcode for that. Simple binding is the class where this method exists. The bootstrap method we're using is called simple bootstrap. And then the signature is returning a call site. receiving a lookup so that we can go and find static methods, virtual methods, so on, the name that was given at the call site, foo in this case, and then whatever the type was. In this case, just returning a string. Here is our simple bootstrap. This is what the JVM will call the first time encounters our Invokedynamic. And it's very simple. In this case, it's never going to change. All we do is find that static method named foo with the type of returning string, stick it into a constant call site object, and return that. Now, this code will never be invoked again. The JVM will always now go straight through to the foo method and never hit our bootstrap logic. So the first call actually does hit the bootstrap, wires it all up. The subsequent calls will just go straight through. So that's the most trivial case I could come up with for using Invokedynamic plus the handles together. So the second one would be modifying the call site. In this case, we want to toggle between two different targets. The first time it calls the first method, the second time it calls the second method, and then it goes back to first. First, second, first, second every time, changing whatever method handle is in the call site every time you invoke it. So here's basically our two methods. There's some Invokedynamic logic I'm not showing here, but it'll essentially just jump back and forth between these two every time you invoke it. Here is the JITE code. Invokedynamic first is the one that we want to start with. It's going to return void. All it does is print something out. Here is our handle. The mutable call site bootstrap is the method we're looking for. Looks basically the same as the other bootstrap that we had. Now, the different part here, once we're in our little bootstrapper, instead of using a constant call site, we're using a mutable call site. Now, in order for us to be able to change that after we get out of bootstrap, once we make the call to the first or second methods, we need to insert that into the argument list. So we get our handle to first, we add the lookup and call site objects into it so it can be changed later on, and then we set the target there. And now this is actually an example of where invoke binder tends to look a little bit cleaner. Here's the version using invoke binder. So starting from a method that returns void, that's the signature we've got, binder.fromVoid, insert at the 0 position in the argument list the lookup object and the mutable call site so that they're passed along as well. And then do the static invocation of whatever the method was that we're looking for, the first method in this case when we start out. Now, the actual implementation of first, you can see we've got the lookup argument and the MCS, the mutable call site argument, on the argument list. And each time we invoke the first method, we're going to grab a handle to the second method, put that back into the call site. So we've replaced it. Next time it's invoked, it'll call the second method instead of the first method. And of course, the second method implementation is almost identical, but it goes back to the first method again. So each time we call, it's just changing the target that's going to be invoked. So now, the more interesting case, the final case of actually having a dynamic language we can play with. What if we don't know the target at compile time? It might be determined based on some runtime type. It might be determined based on some string that's loaded at runtime. We have to look it up after the bootstrap process because we need those arguments to actually be passed in. And then rebind it once we've got the method and do our invocation from then on. So I present to you the latest JVM language, StupidScript. I'm sure you'll all run right out and want to try this. There's a full implementation of StupidScript in the repository. The operations here push a string onto the stack. There's only one type of object in StupidScript, a string. You can send with any number of arguments, and it just pops that many off the stack and does the call. So, for example, a one-arg call would have print on the stack as the method we want to invoke, and hello world as the argument we're going to pass to it. There's a way to def a method. So def n, if we do a def 0, it's a method that takes 0 arguments. If we do def 1, it takes 1 argument. Basically, it just takes those arguments, does the operations we've defined inside it, and then returns. And there is only one built-in operation, one built-in function, which is print, and essentially just does system out print line. So our implementation, as it is, would be with any language. We've got a simple parser that generates an AST. Our compiler walks the AST and emits all the bytecodes. The push operation, the send operation for our invoke, and does the definition of a method within our .class file. A couple examples of what StupidScript actually looks like. Here's the simplest hello world. Push hello world on the stack, push print on the stack. We now have the method name we want to call and the argument we want to pass. Send by popping one additional argument off of the stack. Defining a little hello function that does that for us. Again, fairly simple. If we want to invoke that, similar to before, but hello doesn't take any arguments, send 0, and we do our call. Here is the main part of the StupidScript implementation. Read the file in. I'll gloss over most of the details of parsing. We'll just say that string.split is a very simple way to write your own parser. And then pass the AST into the compiler so we can get a runnable object out and invoke it. Here is the main part of the compiler. Based on whatever the AST node is, if it's a push, we're going to do the JVM push operation, load a constant onto the stack. If it's a def0, we're going to go back into the compiler, create a new method with that method's name that takes 0 arguments. Def0, do the same thing, generate a method that takes 1 argument. And then the interesting one, the send operation here, based on how many arguments we have coming in, the arity of the call, we're going to load the script object so that we can actually invoke methods against it. And then for 0 arguments, we're going to do an Invokedynamic that takes the method we want to call and the script object, does the invocation. If it is a single argument call, we're going to take the name of the method, 1 more argument off the stack, and the script, and do all the call together. And both of these are wired up using the same bootstrap logic. Here is the bootstrap method, again returning a call site. We've got a lookup, a method name, and a signature, a type that goes along with it. We've got our mutable call site. We bind it to our send implementation that's actually going to do the logic to look up a method and call it. And then we'll tell the JVM we're ready to go. Now you can do the call. We'll figure it out dynamically at runtime which method we're going to invoke. These are the 2 print built-ins, just so you can kind of see what they look like. And finally, send impl, which is actually the implementation of dynamic dispatch in StupidScript. If it's print, we're just going to go grab the print handle. It doesn't take any arguments, so we're going to drop everything that was passed in. If it's not print, it's not our one built-in function, then we're going to go look up that object, stick it back into the call site, and the JVM will do the invocation for us from then on. So we've basically dynamically at runtime received a method name, looked it up, and done the call, all using Invokedynamic. All right. So that's what I have. Went through it a bit fast. Hopefully you'll be able to review the slides online or watch it on Parlays when it's up. I'd recommend just starting out by playing with method handles. It's fun to play with them, fun to build little function objects. You may see that in some of the more recent builds of the JVM, especially in the OpenJDK 8 side, that method handles do actually start performing quite a bit better than reflective operations. If you want to take the next level, you could start doing your own playing with Invokedynamic bytecode. I have a talk, several videos of it online, JVM bytecode for dummies that'll kind of get you started. If you're already familiar with bytecode, there's not a whole lot for you to do. Generate the bytecode, write the bootstrap method, and you've got Invokedynamic working. If you got any questions, you can follow me and ping me online or email me, headius@headius.com, simple enough. Try out JRuby. It's probably definitely the first or earliest adopter of Invokedynamic, and I think we're probably using it more than any of the other mainstream languages at this point. And we've really been pushing the edges of performance and stability with it. So that's all I have. There's some more contact information for me. I blog about this stuff on blog.hedius.com. Again, you can follow me if you want to ask questions or if you're curious about this, and check out the code. And I think we've got 6 minutes for questions. I've blown all your minds. Yeah, one over here.
I'm sorry if it's a stupid question. Like in a sort of evil, you evaluate a string and execute the code. There can be some issues, security issues, like in SQL with you have SQL injections. Could there be security issues with Invokedynamic?
Well, it's funny you ask. Some of the recent security issues were actually minor holes that were introduced, specifically into the lookup object. Remember I mentioned the method handles .lookup gives you a special lookup that can see private methods, private fields, and so on. So one of the exploits that was fixed recently was actually related to that. It was giving too much access and hiding some security details from the JVM. Now, as far as the dynamic side of it wiring up an Invokedynamic, it's as secure as the bootstrap logic you put behind it, which is what you define. So you could certainly introduce a security issue of your own, but that's not really unusual. It's not really different than any other code you might write. It still is going to be code you're generating. You programmatically build up these method handles. And in fact, in some cases, it may actually be more secure than doing your own runtime bytecode generation because you're not having to deal with the issues of managing the stack, managing the arguments that are coming in, and getting all that right code into the bytecode. You can do it as part of the method handles. It makes it a little bit easier to track. So yeah, I mean, like anything, you can introduce a security issue with it, but it's no more insecure than anything else that's on the JVM, modulo any implementation issues at the JVM level. Other questions? Yes, Remy.
Just a small one. Just currently there is an API. We have delivered something. What do you want? If we go back, what do you want to change, if it was possible?
No. So in the method handles API specifically, what would I want to change, or in general?
In general.
Well, I have my number one thing I would like to change. You can represent almost everything you would write in Java code using method handles and the adaptations that go around them, except a backward branch. So it is impossible for you to have a method handle chain that would be a loop, for example, which would be very useful. With that, I believe method handles would actually be Turing complete, and we could actually translate code just using method handles and not generating any bytecode at all. That's one thing I would really like to see, is a Boolean loop construct added to the method handle API. Other than that, you know, the work I've done on invoke binder, you know, if you get into the functional mindset where you're getting a function object and you're currying some values into it and doing some modifications that wrap around it, you can do that. You can follow the API, but for a typical Java developer or typical imperative programming developer, you think about it the other direction. I've got arguments coming in. I want to change a couple of them. I want to reorder them and then do the call. I don't know if that's something that needs to change in the method handles API to be able to go top down rather than bottom up, but it's something that always still kind of trips me up in the process of using the method handles in the current implementation. I guess that's probably about it. I'll think about that a little bit more. Yes, over here.
Can you recall, I know that virtual methods are far less fast than static method invocations. Can you recall the hierarchy between the different types of invocations, and I'm sorry if maybe I didn't understand, but do Invokedynamics can clear those differences?
Okay, so question is basically the difference in performance between the different invocation types, and then essentially what does Invokedynamic look like as far as the performance of a call. Well, in the current implementation, I'm going to try and go up here to this view, and we'll make it big again. Magic animations. Okay, so here are our operations, and you know the overhead involved in each of these operations you can kind of see based on what it has to do. There's a little bit more visibility checking that happens in the invoke special case. There's no type checking of the target object in the invoke static case. As a result, invoke static can be a little bit faster. Invoke special can sometimes be a little bit slower. So yes, you can see that there's differences between these, but when it comes down to the Invokedynamic side, there is a little bit of overhead depending on which kind of call site you're using. Constant call site will go straight through the JVM, will just optimize it right away as if it were a static call, depending on what the handles do. If it's a mutable call site, it's about the same amount of overhead as for a virtual invocation. The JVM still has to verify every time that we've got the right target objects, that we've got the right argument types. And it's pretty close to the point where the JVM will actually optimize it about as well as a virtual invocation. The static side, it's kind of in between somewhere. It's not quite as fast as doing a straight up static invocation because it still does do some of the method handle checking, method handle logic at the call site level, but it's getting close. The original promise that John Rose made to us developers was that he wanted Invokedynamic to be at least no slower than an interface invocation, and ideally as fast as a virtual or static invocation. And they're working towards that. They're getting very close to that at this point. And that's about all I have as far as time. Thanks very much. Feel free to email or ping me online.